So for the rational zeros theorem, we're looking for the zeros of this function. That means we're looking for where this graph crosses the x-axis. And because the degree is 4 and the leading coefficient is a positive 2, we can kind of assume or know that the graph looks something like this. And it's possible that it crosses the x-axis 1, 2, 3, 4 times because my degree is 4. But that's just an assumption. We don't really know because we don't get to use decimals on this problem. But we still have to find the zero somehow. And so the theorem is that if you look for all the factors of your constant, which happens to be 18, so I have 18 on top and my factors are 1 times 18, 2 times 9, 3 times 6. And then you find all your factors for the leading coefficient, which is 2. So my leader is 2 and my factors are 1 times 2. We're going to do a rational, that means a fraction, where the constant goes first and then the leading coefficient goes next. So we're going to start with 1. 1 goes on top. We're going to do constants on top, leading coefficients on the bottom. So we're going to start with the 1 on the constant, and it's going to go on top of this one and on top of that 2. So 1 over 1, 1 over 2. We took care of that one. So now we're going to go on to the 2, and it's going to do the same thing. 2 over 1, 2 over 2. And we're going to repeat the process with the rest of the factors. So now 3 over 1, 3 over 2. Move on to the next one, 6 over 1, 6 over 2. The next one will be 9, so 9 over 1, 9 over 2. And then 18 over 1, 18 over 2. So what I did is I created a list of all the possible zeros for this function. And we need to clean them out. That means anything that repeats, we don't have to write it twice. And because I have a positive number, I would also have the negative version of it. So this first rational is 1 over 1, or is just 1. So my possible root would be x equals 1, but it could also be negative 1. So we can do a plus or minus 1. So that's going to be this first one. For the next one, I have 1/2, so positive or negative 1/2. The next one is 2 over 1, so positive or negative 2. And then 2 over 2, I don't really have to write it because 2 over 2 is the same thing as 1. So I'll move on to the 3. 3 over 2, 6. 6 over 2 is the same thing as 3, so I don't have to write that one. And then I have 9, so plus or minus 9, plus or minus 9 over 2, plus or minus 18, and then 18 over 2 is the same thing as 9, so I don't have to write that. So these are the list of all the possible roots that this polynomial can have. But remember, it only has 4, so I would have to guess and check until I find which of the 4 are the correct ones. Here we have another example. We're going to do the same thing. We start by finding the constant. I like to do the constant first because we have the constant on top, leading coefficient on the bottom. So I do the constant, which is 25 first. 1 times 25, 5 times 5. And then I do the leading coefficient, which is 2. I don't really care about the negative sign because remember, at the end, we add the plus and minus, so the sign will come at the end. Again, we do the constant on top, so we're going to start with the 1, on top of 1, and on top of 2. The 5 on top of 1, and on top of 2. I don't have to repeat the 5, so move on to the 25, on top of 1, and on top of 2. This is a cubic, or not a cubic, a quintic function because the exponent is 5, so it should have 5 in total. But my possible for now are plus and minus 1, plus and minus 1/2, plus and minus 5, plus and minus 5/2, plus and minus 25, and 25 over 2. We can keep doing this if you want to, but that's the general gist. Finding the rational or using the rational root theorem, it's not that bad. It just takes a long time, and you might have to guess and check quite a few times before you find the actual roots. And then to find the roots, which is the exciting part, normally we would do division, either long division or synthetic division at first. I prefer synthetic division just because it can, like, especially when you're doing the whole numbers, I would always try plus or minus 1 first or plus or minus 2, like the easy numbers. Skip the fractions for now because we don't want to do that in synthetic. But then when you get to a quadratic, like once you factor a polynomial that looks like this a few times using synthetic division, and then you get to a quadratic, it's easier to do the exposal, right? Like you can try and do the exposal where your a value is 1, 3, and c is 4. 1 times 4 is 4, and 3 on the bottom. If you try to figure out what numbers multiply to get 4, but add up to 3, you're going to notice that nothing works. So exposal does not work for this problem. That means you have to find a different method. In this case, I would prefer to do the quadratic formula because it works all the time. So I know that first I would find the discriminant because that tells me so much about my roots. It tells me what type of roots I would have. So my discriminant would be b squared minus 4ac, where b is 3. So 3 squared minus 4 times a, which is 1, and c, which is 4. 3 squared is 9, minus 4 times 1 times 4, that's 16. And that looks like it's going to be a negative 7. So because my discriminant is negative, that means I'm going to have 2 complex roots because it's a negative discriminant. That means that I don't actually cross the x-axis. My answer should have an I somewhere because they're imaginary roots. And to find those imaginary roots, we do negative b plus or minus square root of d over 2a. Where negative b means we just change the sign on the b value. We have plus or minus the square root of the discriminant, which is negative 7, over 2 times a, which was 1. So if I clean things up, I have negative 3 plus or minus I square root of 7 over 2, because every time you have a negative instead of a square root, we take it out as an I, and we can't simplify 7. It's a prime number, so it gets to stay inside. From here, I just have to separate the real from the imaginary. That means that this is the real part of the equation or the root, and this is the imaginary part of the actual root. Again, complex roots come in pairs. So you have the positive part of this root and then the negative. That's why it's plus and minus. So here's another example. Again, if you try to do exposal, we have 3, negative 5, and 1. So 3 and negative 5 does not work again. So discriminant would be b squared minus 4ac. b is negative 5 squared minus 4 times 3 times 1. Negative 5 squared is 25 minus 4 times 3 times 1, that's 12. So I get 13. So because it's positive, that means I will get 2 real roots. So it will cross the x-axis, but it's going to be some type of decimal. Just because it's a 13, and 13 is also prime. So we can't really take the square root of it when we put it into this formula. So I have negative the b value plus or minus square root of the discriminant, which is 13, over 2 times a, which is 3. So I clean up the parentheses. Negative negative makes a positive 5. So 5 plus or minus square root of 13 over 2 times 3, which is 6. So I have 2 roots. One of them is 5 plus or minus square root of 13 over 6. And the other one is 5 minus square root of 13 over 6. So 2 real roots. Last example, A, B, C. A times C is 6. B is 7. For this one, luckily it does work. 1 times 6 is 6. 1 plus 6 is 7. So I have 2 roots. To find them, first I start with the factors. I set those factors equal to 0. And I solve for x. X plus 6 equals 0. Subtract 6. X equals negative 6. So those are my roots. X equals negative 1 and negative 6. So this one's a lot easier.